In this video, I introduce mean field approximation for sigmoid belief networks. Bayesian belief networks provide a rich graphical representation of probabilistic models. The nodes in BBNs represent random variables, while the connections represent causal influences. Learning and inference require computing the joint probability Px on the BBN nodes, which is equal to product of conditional probability of each node xi, where the conditional probability P is here. PA stands for parent. However, it's intractable to compute the joint probability for practical problems. Bayesian rule is used to convert the joint probability into likelihood. And then mean field approximation is applied to compute the lower band of likelihood. The maximum likelihood is converted into maximizing its lower band. Suppose that a Bayesian belief network is defined over binary random variables S. The parents of Si are denoted as PA here. In sigmoid belief network, the probability that the node I is activated is given by here, sigmoid function. The conditional probability of Si is written in a general formulation here, which becomes a sigmoid function if Si is 1. The joint probability PS over all nodes in sigmoid belief network is written as here. The nodes S in network are either visible units V or hidden units H. Using Bayesian theory, the conditional probability of a hidden unit H given visible unit V is computed here, where PV is a partition function of the visible units V. In principle, the partition can be computed by marginalizing joint probability over hidden units H. However, it is impossible because we cannot directly calculate PV or conditional probability P of H given V. Approximation technique such as mean field approximation is used to compute them. Mean field approximation is a statistical mechanism model. For example, random variables Si represent the localized magnetic moment, and the sum here represents the local magnetic field. The central limit theory is applied to these sums, and then mean field theory ignores fluctuations and replaces these sums with their mean value. The joint distribution PS is written as here, where PV is the likelihood of the evidence V. Mean field theory is used to obtain the approximation Q for the conditional distribution and provides a lower band of likelihood. For any approximation distribution Q, we have the equality here. Using Jensen's inequality, we have this lower band. Using the chain rule, the difference between the left-hand side and the right-hand side is a Kullback-Leibler divergence, which is the difference between low band and this sum over H. Obtaining Q, minimizing the KL divergence. The lower band includes two terms. One is mean field entropy, one is mean field energy. The first term measures the uncertainty in the mean field distribution, and the second term measures the probability distribution in the belief network. The mean field approximation represents H as a Bernoulli distribution with a mean mu I of binary hidden units S in this formulation. The mean mu I is selected to minimize KL divergence, which is equivalent to minimize the difference between the true log likelihood and the lower band of mean field. The mean field band on log likelihood of the evidence V is obtained by submitting Q here. The lower band P larger than LV, where LV is the objective function, which includes the three terms. The first term is a mean field energy. Second term is expectation over the mean field. And the third term is a mean field entropy. For more details, please check with these references. Thank you. Bye.